Del operator, it is a differential operator. Now, del operator, three del operators are there in Cartesian coordinate system, in cylindrical coordinate system, and in spherical coordinate system, because coordinates are changing in different coordinate systems. So this is it is in Cartesian coordinate system. Okay, so one by one we can see. Now here in cylindrical coordinate system, you have to write. Now in cylindrical coordinate system, coordinates are rho, phi, and z. Okay, these three coordinates are there. So del differential operator, deba by deba rho, a rho cap, plus 1 upon rho deba by deba phi. Now here there is one trick to remember, that what is the differential length of 5? It is rho into d phi. Okay, so take that differential length at the denominator side, that is the rho d phi, but here it is the differential, that is the partial differentiation. So rho deba phi. So 1 upon rho deba by deba phi, a phi cap, plus deba by deba z, a z cap. This is the del operator in cylindrical coordinate system. Del operator in spherical coordinate system. Again, coordinates are r, theta, phi. So, deba by deba r, ar cap, plus for theta, what is the differential length? It is r d theta. So, at the denominator side, 1 upon r deba by deba theta, a theta cap, plus what is the differential length for phi? R sine theta deba phi, right? Na d phi. So 1 upon r sine theta deba phi, deba by deba phi, a phi cap. So del operator in cylindrical coordinates and del operator in spherical coordinates. Three important formulas. Del in Cartesian, simple deba by deba x, in cylindrical, in spherical. So for this, differential length is very important. Okay, what is the differential length? So according to that, using some tricks, you have to remember this formula, that is the del formula for this cylindrical and for spherical. Then moving forward, like for first operation, that is the simple del v. There is no any dot, no any cross between del and v. Simple v, the operation is known as gradient of scalar. So what is the gradient? So gradient, that is the one term, that is the maximum rate of change of potential. Like the formula dv by dl. As the distance increases, there is a change in the potential. That is the maximum rate of change of v. That is the gradient, and it is denoted by capital G. So what is the practical example for that? In a cable. So in a cable, potential is a scalar quantity. Yes, obviously V is a scalar quantity. But rate of change of potential, it is a vector E bar, that is the electric field created. So that's why when we apply del operator on a scalar quantity V, the result is a vector quantity. So that's why in terms of this, with the help of this example, this is the, it is, I think will be clear to you that potential is a scalar quantity, but rate of change of potential dv by dl, what we get? Electric field. जो केबल में पोटेंशियल चेंज होता है उससे इलेक्ट्रिक फील्ड जनरेट होता है, तो दैट इज द वेक्टर ई बार. That is the gradient of scalar field V is a vector that represents both the magnitude and direction of maximum space rate of increase of V. This is the definition of the gradient of V. And the formulas are del V. Simple. In the del operator formula, put V here and here. It is a scalar quantity. There is no any dot and cross product is there. Simple. In cylindrical, del formula, put V. Same. For spherical coordinate system. So, gradient, output of the gradient field is a vector quantity. This is the gradient. Okay.